Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
For more than 4 decades, humanity's most distant explorers have been silently drifting away from Earth, far beyond the planets, beyond the sun's influence, and into regions no spacecraft was ever meant to survive. Voyager 1 and Voyager 2 were never designed to last this long, never meant to reach this far, and certainly never expected to send data from the edge of the solar system itself. Yet today, against every expectation, Voyager 1 is speaking again. What it is detecting out there is forcing scientists to rethink where our solar system truly ends and what waits beyond it. If you enjoy deep space documentaries that uncover the hidden structure of our universe, make sure to subscribe, because the story of Voyager is far from over. The most distant human-made object, Voyager 1 is not just far away, it is the most distant object humanity has ever built. More than 15 billion miles from Earth, it exists in an environment completely unlike anything encountered before. In late 2023, something unexpected happened. The probe began transmitting data that made no sense. The signals were fragmented, disordered, and unreadable. There was no recognizable telemetry, no clear measurements, no usable information. At first, engineers suspected a simple malfunction, but the deeper they looked, the stranger it became. After weeks of analysis, NASA engineers traced the issue to a corrupted section of Voyager's memory. A single chip, and smaller than a fingernail, had likely been damaged by cosmic radiation. Out there, beyond the protective bubble of the solar system, high-energy particles slam into spacecraft constantly. These particles can flip bits, scramble memory, and quietly destroy critical systems. Voyager was still alive, still transmitting, but its brain had been partially damaged, fixing the unfixable from billions of miles away. Voyager 1 was never designed to be repaired. Its flight data subsystem runs on less than 70 kilobytes of memory, less than a modern digital watch. The software had not been updated in decades. There were no backups, no alternate processors, no emergency recovery protocols. And yet, NASA attempted something no one had ever done before: reprogramming a spacecraft across interstellar space. Each command sent to Voyager takes roughly 22 hours to arrive. Each response takes another 22 hours to return. Engineers had to manually rewrite commands in raw binary, assign them to new memory locations, and send them in fragments. One mistake could permanently silence the probe. After weeks of trial, silence, and failed attempts, a signal finally returned. Clean, structured, and readable. Voyager 1 had recovered. A spacecraft built in the 1970s had just performed a system-level recovery operation no modern probe was ever designed to attempt. A mission never meant to last Voyager's story began in 1977. 2 nearly identical probes, Voyager 1 and Voyager 2, were launched from Earth during a rare planetary alignment that occurs once every 176 years. This alignment allowed the spacecraft to use gravitational assists, slingshotting from one gas giant to the next while conserving fuel. The mission was ambitious but short-term. Both probes were expected to operate for no more than 5 years. Voyager 2 launched first, followed by Voyager 1, just 16 days later. Despite launching second, Voyager 1 travelled faster and overtook its twin. Both spacecraft relied on nuclear batteries called radioisotope thermoelectric generators, converting heat from radioactive decay into electricity. There were no solar panels. Sunlight fades too quickly beyond the outer planets. These generators provided only a slow trickle of power, just enough to keep the probes alive. Jupiter and Saturn, worlds that changed science. In 1979, Voyager 1 reached Jupiter. What it found shattered expectations. Jupiter was not a quiet gas giant. It was a violent world surrounded by intense radiation, capable of damaging spacecraft in hours. Voyager survived and delivered discoveries that rewrote textbooks. It detected massive magnetic fields, faint rings, and powerful plasma waves. Then came one of the mission's biggest surprises: Io. Io, one of Jupiter's moons, was expected to be lifeless. Instead, Voyager found active volcanoes erupting with such force that molten material was being blasted hundreds of kilometers into space. It was the first time active volcanism had ever been observed beyond Earth. At Saturn, Voyager revealed that the planet's rings were far more complex than anyone imagined. Braided structures, hidden gaps, and gravitational interactions with unseen moons created patterns never predicted by theory. Even more surprising was Titan. Saturn's largest moon possessed a thick atmosphere filled with organic chemicals, a possible window into what early Earth may have looked like billions of years ago. Voyager 2's extended journey. While Voyager 1 turned toward deep space, Voyager 2 continued onward. In 1986, it became the first, and still the only, spacecraft to visit Uranus up close. Uranus defied expectations. It was tilted almost completely on its side, with a magnetic field twisted into a bizarre configuration, unlike anything seen before. Voyager 2 discovered new moons, faint rings, and a planet that refused to follow established models. In 1989, Voyager 2 reached Neptune. What it found was a world of extreme violence. Winds screamed across the planet faster than the speed of sound. Massive storms churned through its atmosphere. At Triton, Neptune's largest moon, Voyager detected geysers spraying nitrogen into space, a surface with few craters and signs of recent geological activity. It was a frozen world that looked strangely alive. Beyond the planets, the edge of the solar system. After Neptune, there were no more destinations. No moons, no rings, no planets. Voyager 1 continued into darkness. But what scientists once called nothing turned out to be one of the most complex regions ever encountered. The edge of the solar system is not a clean boundary. It is defined by the heliosphere, a vast bubble created by the solar wind pushing against the interstellar medium. For decades, scientists debated what this boundary would look like. A smooth transition? A sharp wall? No one knew. Then, in 2012, Voyager 1's instruments recorded dramatic changes. Particle counts dropped. Magnetic fields shifted. Plasma density spiked. Voyager 1 had crossed the heliopause, becoming the first human-made object to enter interstellar space. 2 Voyagers, 2 different exits. 6 years later, Voyager 2 followed. But the data didn't match. Voyager 1 encountered dense, compressed regions of particles, almost like invisible walls. Voyager 2 found something else entirely. Long streams of particles stretching hundreds of millions of kilometers. Same boundary, 2 completely different environments. Voyager 2 still had a working plasma instrument, and what it detected stunned scientists. The interstellar medium was far hotter than expected, nearly 30,000 degrees Celsius. Yet it was so thin that the probe felt nothing, drifting through it like a submarine through fog. Even more surprising, the heliosphere wasn't smooth. It was wrinkled, folded, and dynamic, shaped by waves of solar energy pushing and pulling at its edges. The glitch that almost ended everything for years. The Voyagers seemed unstoppable. They had survived planetary radiation belts and solar storms and decades of cosmic bombardment. Long after their original mission timelines had expired, they were still transmitting, still functioning, still pushing farther into the unknown. But in late 2022, something changed. And this time, it wasn't subtle. Voyager 1 suddenly began sending back data that made no sense at all. The signal itself was strong and clear, but the information inside it was meaningless. Streams of ones and zeros arrived in patterns that didn't match any known telemetry format. Instruments appeared to be reporting values that violated basic physical limits. At first, engineers hoped it was a temporary glitch, perhaps interference or a minor sensor issue caused by cosmic radiation. But days turned into weeks and the data never corrected itself. The terrifying realization set in. Voyager 1 wasn't just malfunctioning. Its internal memory, the system responsible for organizing all scientific data before transmission, was failing. A computer frozen in the 1970s. At the heart of the problem was the flight data subsystem, an ancient computer built with technology that no longer exists. It hadn't been touched, modified, or repaired since the 1970s. Many of the engineers who designed it had long since retired, and some were no longer alive. Documentation was incomplete. Schematics were buried in old archives. Replacement parts were impossible. Voyager's memory wasn't corrupted in a dramatic way. There was no explosion, no sudden shutdown. Just a few damaged bits. Tiny fragments of memory silently altered by high-energy, particles from interstellar space. But those few bits were enough to break the system's logic. Voyager was alive but confused, talking but not making sense. And there was no way to physically fix it. Rewriting a spacecraft across interstellar space. NASA's Jet Propulsion Laboratory faced an impossible choice. Let Voyager fade into silence or attempt something no one had ever done. They chose the impossible. Engineers decided to rewrite Voyager's memory line by line and move all critical instructions into a different, undamaged section of the system. This wasn't software as we know it today. There were no compilers, no updates, no safety nets. Every command had to be written in raw binary, manually calculated and transmitted in fragments.